Welcome to Learning to Engineer. What is an operational amplifier? Operational amplifier is a device which will amplify the different signal between two inputs and reduce or eliminate the common signal between them. This is what an op-amp was intentionally designed for. So far, throughout these videos in this playlist, we have been seeing op-amp as an ideal device which is said to behave exactly like how it was expected. But in practice, there were many noise voltages lost due to interference and other things that was happening inside the circuit. So there were some signal conditioning circuitry that was placed in addition to the difference amplifier, because of which we have to consider the practical implications of these circuits over the output voltage and the input voltage too. So far, we have been seeing that the difference in voltage between the inputs will be zero when two inputs are same. But in practice, that's not so. Again, we saw that the currents that was entering into the terminals of an op-amp was zero. Again, this is not true in the practical scenario. Now, we are going to focus in detail about the practical aspects of an op-amp in this video. Consider this op-amp IC with the negative and positive terminals, and we have one output terminal which we'll label it as Vout, and let us say, for example, we are grounding both these terminals. There is no signal input applied to it. We are only going to give the plus VCC and the minus VEE. These are the operational supplies of the op-amp. This is just like having only the battery in your phone without giving any voice input or signal input to it. So ideally, the output should be zero because there is no input that is supplied via these terminals, right? But in practice, due to the internal circuitry of this op-amp, there will be a very small difference voltage between the plus and the minus terminals, and this is called as the input offset voltage of an op-amp. This is a constant voltage which can be found in the data sheets of the device. Whichever model of op-amp that you are choosing, you need to browse for that manufacturer's website and download its data sheets to find out the input offset voltage of that particular op-amp. Okay, so that when you are using this op-amp IC in your circuit, you need to know how much voltage will be there when there is no input at all, so that you should do some compensation, maybe through a resistor. Okay, so that you have to do a certain compensation so that you get 0 volt at the output when 0 input is applied at the input terminals. I have a question for you. When the ideal characteristics are varying because of the signal conditioning and other circuits of an op-amp, why are we using an ideal op-amp behavior still? We can straight away go to the practical characteristics, right? So why do we exactly go and learn about the ideal behavior and use even those concepts to solve problems? Why is that? This is because the deviation is very small, that the practical op-amp is closely behaving as an ideal op-amp. In recent technology, these parameters are very carefully designed such that they resemble the ideal behavior, and when you see a bird's eye view of your overall project or overall application, you can observe that the output voltage that you get via this op-amp will be approximately same as that of the practical op-amp scenario. When you are thinking about the project as a overall, you can consider the ideal behavior of an op-amp. Whereas when you are trimming it down to a level where you are calculating the value of the resistors and finding out which resistor will exactly suit this application and all, for those kind of applications, you need to understand the practical aspects too, so that you will be able to go into the specifics of your circuit. Next, we will see about the input bias current. So far, we have been saying that the current that is entering into the terminals of an op-amp is zero. But in practice, that is not the case. When we are not applying any signal input and we are just powering on the operational supply, we are just powering on the plus VCC and minus VEE, and in this case there is a very small input current that is entering into these two terminals of an op-amp, and in fact the interesting thing is these two currents are not the same. They will be approximately same but not exactly same. Okay. Let us call them to be IB1 and IB2. IB1 will be approximately equal to IB2 but not exactly same. So what is input bias current? It will be the average of these two currents. IB1 plus this is B. IB1 plus IB2 divided by 2. This is the input bias current. There is one term in this operational amplifier's characteristics. There is a small difference between IB1 and IB2, right? What is this difference called? Type that down in the comments. Okay? I want you all to go into the data sheets, check out what the input bias current is and find out the difference between them. Okay? You will be observing that it's very small. Okay? So next we are going to talk about the common mode rejection ratio. The common mode rejection ratio is the ratio of the differential gain to that of the common mode gain. We usually saw one thing, right? From the beginning we have been seeing what an operational amplifier is. The op-amp will amplify the difference signal and that gain is called as the difference gain of that op-amp. How well the op-amp suppresses the common signal, that gain is called as the common mode gain of an op-amp. Okay? To make things easier, consider this scenario. I have an op-amp, there is a negative terminal, there is a positive terminal, and to both these terminals, what I am doing is, I am connecting the same supply. Let's call it to be VA. Okay? I am connecting VA to both these. Usually we will only be connecting the power supply to either of these terminals and we will measure the output, right? But now I am connecting the same power supply to both these terminals. Okay? So being an ideal op-amp, what will the difference signal be? The difference signal will be 0 and hence the output voltage will also be 0 volt. But in practice, that's not the case. Okay? There is a common mode gain associated with it which will also contribute to the output of the op-amp. The output of the op-amp is actually the differential gain into the difference in the inputs plus the common mode gain ACM into the common inputs. I am just writing it as BCM. Okay, this is the actual output equation of an op-amp. So far we have been considering only this part of the op-amp for ideal scenario. When we are considering the practical things also, when we have to consider the common mode aspect of an op-amp too, and this is the practical equation of an op-amp. PRACTICAL. Yeah. Okay. This is the practical operation of an op-amp, and the common mode gain will be the output at the terminal due to this common input voltage. I am denoting it as VOC divided by VA, which is the common input which is applied. VA is the common input in this case and VOC is the common output in this case. Okay. So what is the common mode gain? It is VOC divided by VA. Okay. So I'll just put a pause to the concepts of this. We are going to solve one problem with the parameters that we just learned. Okay. And after this problem, we will be seeing about two more parameters which will affect the ideal nature of an op-amp. Okay. The question is, a differential amplifier with signal terminals X, Y and Z is connected as shown in the figure A. This is figure A, okay, for CMRR measurement, where the differential amplifier has an additional constant offset voltage in the output. Okay, so it means that in the output, in addition to what your input is going to contribute, there is going to be additional component which is called as a constant output offset voltage. Okay, the observations are when Vi is 2 volt, Vo is 3 millivolt, and when Vi is 3 volt, Vo is 4 millivolt. Okay, the question is, assuming the differential gain to be 10 and the op-amp to be otherwise ideal, what is the CMRR? We have 4 options that's given to us. We just learnt one thing, that the common mode rejection ratio CMRR is the differential gain divided by the common mode gain, right? We are given the value of differential gain, it is 10, and we are asked to find out what the common mode gain is. Okay, we also learned one more thing. What is the common mode gain? It is the ratio of the common mode output voltage to that of the common mode input voltage. Okay, using this information we will find out the gain. Two cases are given to us. In the first case, you see you have an input, common mode input, common mode output. Using this itself we can find out A, right? It is just 3 millivolt by 2. Is it right? No, it's wrong, because they have given that there is a constant offset voltage at the output which will be applicable whatever be the input that you are going to apply. Okay, so let's apply this and formulate a small equation. So the output, common mode output, will be the offset voltage at the output. Let me just put it as VOF plus the common mode gain times the common input. Okay, and for this we have two cases, right? Let's substitute the values. It's given that the output is 3 millivolt when the input is 2 volt in the first case. So we'll just substitute in this equation 3 millivolt, which is 3M, is equal to the output offset voltage plus the constant gain times 2 volt. This is as per case number 1. As per case 2, output voltage is 4 millivolt, which is equal to the offset voltage at the output plus ACM into 3. Let's subtract both of them to kill this common output offset voltage. Okay, so let's subtract equation 1 from 2. You will be getting 1 millivolt is equal to ACM. Okay, so this is equal to 1 into 10 to the power minus 3. Superb, we got the value of common mode gain. Okay, what is asked? CMRR is asked. The common mode rejection ratio will be the ratio of differential gain to that of the common mode gain. It's given that the differential gain is 10, so it is 10 divided by 10 to the power minus 3. So the CMRR is 10 power 4. Okay. Now we will see two more parameters which will affect the ideal nature of an op-amp. These parameters are linked with the frequency. Okay, it is linked with the frequency aspects of op-amp. We have been believing so far that the gain of the op-amp or the DC gain is constant throughout the operation. That's not the case. Okay. Only as long your frequency is within the cutoff frequency, your gain is going to be constant. Okay, let's see how this behaves. We'll draw the frequency on the x-axis and the gain on the y-axis. The gain, let us call it as AOL, is going to be constant only up to a certain frequency, and beyond which it will reduce to unity. The gain of an operational amplifier can never become 0 because it means that the output is going to be 0, right? The output voltage is AOL times the input ideally. Okay, so this gain can be equal to 1 maximum because output voltage can be 1 into input, which is input. So at the worst case, the output will be exactly as that of input, but it will never be 0. So remember that point. This is 1 and not 0. And the frequency at which this gain falls by 3 dB is called as FC, or the cut-off frequency. Okay, and this frequency at which the gain falls to 1 is called as the unity gain bandwidth or the unity gain frequency. This frequency at which this happens is called as the unity gain frequency, and if you are seeing it from 0 to f1, this op-amp can be operatable, and this bandwidth is called as the unity gain bandwidth. Okay, so the unity gain bandwidth will be the constant or the open loop gain of the op-amp times the cutoff frequency. When we are measuring the frequency aspects, we talk in terms of slew rate and the maximum frequency of operation, because we have seen that over a wide range of frequencies the operational amplifier gain is not 1, okay, because the range is very high. The unity gain bandwidth, I mean this frequency is usually in megahertz or something, even more than that. So it is a very wide range. So what is the maximum frequency at which it can be optimally used? We are going to see about these two parameters. The slew rate, or SR in short, is defined as the rate of change of output voltage with time. Okay, how quickly the operational amplifiers changes its output, that is called as the slew rate, and it is vastly affected by the input signal's frequency. Next thing is the maximum frequency of operation. Let's find that out. Okay, let us consider that you have a signal output which is a little like sinusoidal. You have it as k sine 2 pi f into t. Okay, because any signal can be formulated into sinusoids, maybe DC, maybe AC, and that is the whole concept of Fourier transform. Correct? So, okay, we'll talk about this Fourier transform concept in the later videos. Now we will see about the maximum frequency of operation. Let us consider V naught to be in the sinusoid form. What is the maximum change that is possible through this signal? We have to differentiate and find out. So when we differentiate, this is k cos 2 pi f into t into 2 pi f. The maximum rate of change of output is what we are trying to find in order to be able to find out the maximum optimum frequency of this to get this output. Okay, so I'll break this down into another step. This at max is going to be the maximum value of cos. Okay, because this is a constant, this term is a constant, this is also going to be a constant. Only the variable term is this. And you all know that the maximum value of cos is 1. All the trigonometric ratios are from 0 to 1 except for tan 90, which is infinity. Okay, we'll push that part aside and come to this video. Okay, so the cos value ranges from 0 to 1 and the maximum value of it is 1. So when we are trying to find out the maximum rate of change of input, we are going to substitute the value of this term to be 1. Okay, so this is equal to k into 1 into 2 pi f. Let's denote this as f dash. Okay, because this is going to be the maximum frequency at which you get a maximum change of in output. Okay, and this is also called as slew rate, which we just saw, right? So the slew rate is equal to k into 2 pi f dash, and what is f dash now? This will be slew rate divided by k into 2 pi, and this is in the unit of hertz. When we are talking in terms of angular frequency, let's denote this to be omega dash, which is slew rate divided by k, and the unit is in radian per second. Okay, so these are the two parameters which we are going to talk in terms of frequency effects of op-amp. This is the slew rate and the maximum frequency of operation. Now we saw two more parameters which will be affecting the ideal behavior of an op-amp, and now let's solve some more problems in this area to understand this even more deeply. If the slew rate of an op-amp is 2 volt per microsecond, what is the maximum closed loop voltage gain that can be used when the input signal varies by 0.5 volt in 10 microseconds? In this question, the slew rate is given to us. The slew rate is given as 2 volt per microsecond, which means that for per microsecond change in time, the output value varies by 2 volt. Okay, and what is the maximum closed loop gain that can be used when the input signal varies by this much? Okay, so what is gain in general? It is output by input, and since we are talking in terms of slew rate, the maximum rate of change of output divided by the maximum rate of change of input will give you the closed loop gain. Okay, and this is nothing but the slew rate divided by the rate of change of input. If we substitute whatever is given to us, we will be getting 2 divided by 10 power minus 6 as slew rate, whole divided by the input signal varies by 0.5 volt in 10 microseconds. So this is 0.5 divided by 10 into 10 to the power minus 6. The gain is 40 volt per volt, or this is the closed loop gain of the op-amp. Okay, now we'll look at one more problem in this concept. If the unity gain bandwidth is 1 megahertz and the closed loop voltage gain is 20 volt per millivolt, what is the cutoff frequency of the op-amp? We saw that the unity gain frequency is equal to the voltage gain times the cutoff frequency. So what is asked? The cutoff frequency is what is asked. Okay, so what is the cutoff frequency? The unity gain frequency divided by AVD. If you just substitute, you will get the answer. It is 1 into 10 to the power 6. So it is 200 volt per millivolt. So if you take this to the numerator, you will be getting 10 to the power 6 divided by 200 into 10 power 3, which is equal to 40 hertz, right? So in this video, we saw 5 parameters that will be affecting the ideal nature of an op-amp, and they can be referred in the data sheets of the op-amp. Usually these are very small, and it is usually close to the ideal parameters that we were assuming so far. Okay, so thanks for watching. If you have any doubts in these topics, you can let me know at learningtoengineer@gmail.com, and don't forget to subscribe to my channel and also ring the notification bell so that you don't miss out my next video. Okay, thank you.